Hello world, I'm Gloria Bambiza. I'm a PhD candidate in computer science at Cornell University. My research is in computer systems and networking. I'm developing technical systems that collect, transmit, and analyze sensor data to support decision-making in rural farms. This work critically explores how networking researchers might inadvertently design fragility into rural infrastructure. This is joint work with Phoebe Sengers and Hakeem Weatherspoon. Social scientists have found that, compared to urban infrastructure, rural infrastructures such as internet tend to be less built out, more prone to breakdown, and less likely to be repaired. This infrastructure fragility stems in part from urban-centered technology design, regulations, and standards. Urban-centered design assumes, for instance, a large population density and easy access to repair infrastructure. Networking researchers are already addressing this fragility of rural infrastructure. The question we explore here is whether or how networking research may be reproducing the fragility. Specifically, we look into new networking infrastructure being designed for digital agriculture, i.e. the collection and processing of data on farms. Digital agriculture, or DA for short, can be viewed as a layer of computing system that unifies sensors, on-farm networking, cloud-based storage, and data processing software such as application programming interfaces, or API, and artificial intelligence, or AI. The system generates decision-making insights that are finally sent to the farmers. Our approach to DA builds on work in values in design, or VID for short. Work in VID has shown how values and societal considerations can be built into computing systems at the early stages of design. This work shows the importance of early engagement with technical decision-making before its societal effects are built in. This is typically done by engaging technical researchers and social scientists in dialogue during infrastructure development. However, according to Shilton, technical researchers find it difficult to discuss the eventual impact of infrastructure that is designed to support a wide variety of applications. In this work, we address this issue by interweaving critical reflection with hands-on system development. This approach, known as critical technical practice, was pioneered by Philip Egri in reforming AI research. Here, we apply it to networking research. Our application of critical technical practice was refined as follows. We spent 24 months deploying experimental DA technologies while documenting our everyday experiences with getting the technology to work. To help mitigate the limitations of relying on our own experience, we conducted an interview study with 6 colleagues building applications with similar technologies. And we included feedback from an ethnographic participant observation of our research meetings. We addressed 2 specific research questions. First, how do researchers and engineers anticipate the potential fragility of rural networking infrastructure in early design stages? Secondly, what consequences might this anticipation have on the eventual infrastructure's fragility? Our work follows a case study of the software-defined farm, or SDF for short. I lead the SDF design and implementation to connect a variety of hardware and software for farm data collection and processing. The SDF addresses challenges of limited connectivity in rural areas. For example, by deploying TV whitespace technology, which repurposes the noise between analog TV channels for reliable internet in remote regions. In our findings, one way that researchers address infrastructure fragility is by producing seamless systems. In building the SDF, I envisioned a platform that will shield applications and the APIs and hardware components they use from each other's details. That is seamless plug and play. Our colleagues similarly had seamless ideas for their eventual systems. For instance, participant 5 describes the expected seamless of his system simply as one of the first products that you install it, you put batteries in the sensors, you go home and see the data. In reality, however, numerous technical challenges emerge from both hardware and software implementations opposing these seamless views. For instance, we could not rely on the intuitive righty-tighty, lefty-loosey aphorism to screw sensors in place. Our colleagues face similar struggles in getting technology to work. For instance, participant 2 describes that, for the first week, he was pulling his hair trying to simply find out the firmware version of his sensors. While the technical challenges were significant, creating functional prototypes required struggles with many other forms of material resistance. For ourselves and our colleagues, this included work like producing inconsistent documentation, or setting up virtual troubleshooting calls, or updating software and debugging hardware components in the field, or negotiating equipment installation with university building managers, or worst of all, digging sensor boxes out of hardened snow. The question these experiences raise is, then, how do researchers and engineers maintain faith in seamless systems despite sinful realities in their daily work? Our analysis shows that this faith is produced through institutional structures that render seams invisible during the course of research production. We show 3 ways in which seams are rendered invisible. First are disappearing seams. This is incidental work that researchers tend to discount because it doesn't contribute to generalizable knowledge claims. For instance, when writing papers, we don't get credit for recovering antennas that were lost in the supply chain. And our colleagues also view these challenges as minor logistical inconveniences. Secondly, we have hidden seams, whereby our organizations shield us from seams that we would otherwise have to deal with. For instance, living in a college town gives me access to 2-day shipping service for sensor battery replacement. This service would likely not be available in a remote farm. Lastly, we have distant seams. These are seams that we as researchers simply don't see because, despite being experts in our own fields, we're not aware of day-to-day farm realities. For example, participant 4, who is a farmer, mentioned that some of his sensor vendors told him to expect 6 months without having to change the batteries. But temperature cycles in his farm made the batteries last only 2 months. Given this prevalence of invisible seams, a reasonable question then is, how should researchers and engineers handle them? We are aware of the seamful nature of rural infrastructure, that is, they're less built out, more prone to breakdown, and less likely to be repaired. Thus, seamlessness could clearly have some benefits. However, an over-reliance on seamlessness may inadvertently reproduce seamful infrastructure that masks the interest of powerful stakeholders in DA. Numerous scholars have shown the prevalence of invisible work done by end users to bridge infrastructural seams. Therefore, researchers should aim to support a more artful management of seams. This artful management enables end users to deal with seams in their own ways once the technology is widely deployed. As a starting point towards this artful management of seams, we propose 3 recommendations in the paper: supporting the right to tinker, documenting early groundwork and its effects on technical decisions, and bridging the gulf between research and commercial farms. For ourselves and our colleagues, visions of seamlessness seemed key to spark the digital agriculture revolution. However, our work suggests that the emerging DA infrastructure is more seamful than we realize or hope. Further, treating seamlessness as an absolute goal could actually exacerbate the very challenges of rural infrastructure we set out to resolve. Instead, while targeting some seamlessness, we recommend leaving room for end users to artfully manage those seams as DA technologies become widely deployed.